In this presentation, I will share our work insightful instance features for 3D instance segmentation. 3D instance segmentation is a fundamental 3D computer vision task that significantly contributes to real-world applications. Given 3D point cloud scenes, the 3DIS task identifies respective instances and assigns semantic class labels with the goal of comprehensively understanding entire spatial environments. Recently, kernel-based and transformer-based approaches have been proposed, aiming to overcome the limitations of traditional frameworks. Kernel-based methods leverage instance-aware kernels for dynamic convolution, which decodes instance masks. On the other hand, transformer-based methods train instance queries to identify features about individual objects using attention mechanisms. In both architectures, models utilize hundreds of instance-wise candidate features to estimate the final instance mask. Despite the significant improvements based on their architectural advantages, they have yet to fully optimize the handling of these numerous candidates and still face several challenges. First, we empirically observe that multiple instance candidates from previous works often encode cues from the same single instance. These candidates are then typically decoded into considerable fragment masks representing different components for each instance, such as the backrest or armrest of the sofa. In this work, to estimate the complete coverage of each instance, we introduce a carefully designed instance-wise knowledge aggregation network, called IKA, which integrates the scattered intelligence from multiple fragments, beyond relying solely on a few fragments based on confidence scores. Specifically, we optimize the correlations among instance-wise candidate features, encouraging the network to be aware of the distributed instance-specific knowledge. IKA enables the network to learn relationships between candidates and aggregate their comprehensive cues, maximizing the benefits of using hundreds of candidates. In addition to IKA, we explore additional avenues to enrich the knowledge of instance-wise candidates. Unlike the human visual cognitive system, which perceives instances with sufficient prior knowledge, the network understands instances depending on their external properties from 3D features. However, point features are frequently unstable, primarily due to ambiguous inherent noises caused by sparse and incomplete point clouds. Consequently, these noises are likely to confuse the models, making it difficult to precisely interpret the specific spatial range and unique appearance of instances. To mitigate the negative impact of such noises, we propose an instance-wise structural guidance network, called ISG, which is specifically designed to improve the structural understanding of instance candidates for 3D instances from point features. Here, we utilize the truncated singular value decomposition algorithm to strengthen essential cues of instance features, such as shapes or boundaries, while explicitly reducing fuzzy noises. Then, we effectively transfer fundamental clues for object cognition from ambiguity-minimized features to corresponding original features based on the cross-correlations between them. Ultimately, our instance features are now highly informative across complex 3D instances with aggregated and structural knowledge from IKA and ISG, respectively. Note that our novel networks can be applied to frameworks that use considerable instance-wise candidates, regardless of model structures, including kernel and transformer-based architectures. This is an overview of our framework. In this video, we describe our instance-wise knowledge enhancement approaches based on the modern kernel-based architecture. Our model consists of four main modules: a sparse convolutional 3D backbone, the instance-wise knowledge aggregation, that relates the scattered information of individual instances, the instance-wise structural guidance that effectively instructs candidates with spatial cues from augmented instance features, and finally, a dynamic convolution network. Note that we also describe our transformer-based architecture in our supplementary material. First, sparse convolutional U-net backbone takes a colored point cloud as input and voxelizes point cloud into voxels to extract point-wise feature maps. Given the point features, the point aggregator samples a set of instance candidate features, referring to point positions based on the farthest point sampling. Specifically, we employ two-stage point aggregator blocks to produce optimal instance features across 3D scenes. In the first stage, n'(k) number of candidates are sampled from full-resolution feature FP, while in the second stage, nk instance features finst are sampled based on the f'inst. In this context, we encourage these numerous instance candidates to be highly informative, improving their understanding of diverse real-world instances. We first propose the instance-wise knowledge aggregation network. Although hundreds of candidates provide practical information for mask prediction, they often represent separate parts of each instance, resulting in fragmented instance masks. With these insights, we focus on associating scattered instance-specific knowledge to fully leverage the advantages of multiple instance candidates. To handle multiple candidates, we first identify those representing the same instance based on their pairwise affinity. Specifically, we compute a correlation matrix IKA using the dot product of finst and its transpose, then normalize this matrix to a range between 0 and 1. Here, we note that candidates representing the same instance yield relatively high correlation values. Thus, based on this correlation matrix, we consider pairwise candidates with correlation values surpassing a predefined threshold tau as fragments from the same instance. Then, we softly guide these candidates by optimizing their correlations, motivated by the success of recent correlation regularization strategies. We extend this approach to further enrich coherence among highly correlated candidate features while also encouraging the network to be aware of scattered cues for each instance. In particular, we dynamically construct a pseudo-binary correlation label matrix where elements of highly correlated pairs in IKA matrix are 1, while the rest are 0 for all candidate pairs. Given IKA matrix and pseudo-binary correlation label matrix, we formulate the element-wise correlation regularization loss Ka. The first term facilitates candidates representing the identical instance closer together in latent space, whereas the second term decreases correlations with unrelated candidates, thereby reducing confusion from irrelevant knowledge. In conclusion, our instance-wise knowledge aggregation approach establishes valuable connections that strengthen solidarity across multiple candidates with scattered cues by regularizing loss Ka. In addition to IKA, we present the instance-wise structural guidance network to further enrich instance candidates. Our goal is to enhance the spatial understanding of instance candidates using structural cues from ambiguity-reduced features. To this end, we utilize a simple yet effective truncated singular value decomposition algorithm to emphasize essential cues from features while filtering out noises. Given f'inst from the first point aggregator, we initially decompose f'inst into three matrices based on SVD, where U and V are the matrices with orthonormal columns, and sigma is a diagonal matrix containing singular values, arranged in the descending order. Typically, the higher singular values in sigma include meaningful information for object cognition, while the lower rank vectors are regarded as less important, potentially causing ambiguity. Then, we preserve only the top T singular values, along with their corresponding singular vectors from U and V, facilitating an ambiguity-reduced yet information-rich representation of the original feature f'inst. Based on both f'inst and f'inst, we sample instance-wise features f'inst and f'inst, respectively, employing the shared second-stage point aggregator. Given f'inst and f'inst, we calculate the cross-correlation matrix ISG and also generate a pseudo-binary correlation label, as in the IKA network. We then effectively transfer structural clues from f'inst, utilizing the correlation regularization loss SG. By optimizing loss SG, we conditionally instruct instance features to incorporate spatial configuration details from clarity-enhanced features, improving discriminative power. We then classify the category of each instance via linear classification head using following cross-entropy loss. Also, we predict instance kernels based on highly informative instance candidate features f'inst through MLPs. Furthermore, each pointwise prediction head processes point feature to generate mask features and axis-aligned bounding boxes as auxiliary information for mask prediction. Finally, the dynamic convolution network produces the final instance mask using instance kernels and mask feature. Our framework is trained by minimizing total loss, where mask loss consists of binary cross-entropy and dice losses. We quantitatively compare our approach with existing state-of-the-art methods on various large-scale datasets, including ScanNet version 2, S3DIS, ScanNet 200, and STPLS3D. Ours generally outperforms prior works, achieving new state-of-the-art scores. These results demonstrate that our proposed IKA and ISG networks effectively address numerous instance-wise candidates. We also evaluate variants of our method with and without IKA and ISG modules based on kernel and transformer-based architectures. As shown in Table 5 and 6, the addition of each module surpasses the score of baseline models across all experiments, regardless of model structure. Moreover, in Table 7, ablative experiments using the IOU metric, closely associated with segmentation performance, validate the significance of our proposed two modules. In addition to quantitative comparison, we qualitatively compare Rs with the latest kernel and transformer-based methods. These qualitative comparisons highlight the superiority of our novel framework. In conclusion, the main contributions of our work are summarized as follows. To extend the benefits of producing multiple instance-wise candidates, we introduce the instance-wise knowledge aggregation network, which associates scattered instance-specific information of the same single instance by optimizing correlations among them. We design the instance-wise structural guidance network to improve the structural knowledge of candidates. Specifically, we use a simple yet strong truncated singular value decomposition process to emphasize essential cues from features while filtering out noises. We analyze the effectiveness of our proposed methods on 4 challenging datasets. Comprehensive experiments across various 3D scenarios demonstrate that Rs achieves new state-of-the-art performance on 3D instance segmentation. Thank you for listening.